Hi, and welcome back to back after the summer break to lecture 8 of this summer course on mathematical and statistical methods for infectious disease outbreaks. So let me start by sharing screen so I don't forget that. So today I will talk about different types of heterogeneities that can be included when you make your models more realistic. Earlier, most of what I have talked about, at least, has been assuming that people behave in a similar way. All people behave in a similar way, both in terms of how susceptible and infectious they are, but also in terms of whom they connect to and mix with. So I would say that there are two different types of heterogeneities. Some that are sort of connected to what happens inside your body, how susceptible you are to disease, and if you get infected, how much infectious agents you exert outside of you. But perhaps even more important is how you mix with each other, both the amount of social contacts that you have and whom you have contact with. So a question is, the earlier results that I've talked about assumed this was not the case. So assuming that people are equally susceptible, infectious, and that they mix uniformly, does this simplification make results useless? I would say that they are important, but they fit reality less. It is less problematic the more infectious a disease is. So probably the most infectious disease around is measles, but there are also lots of other so-called childhood diseases and possibly also influenza and COVID-19, but slightly less, I would say. Whereas in the other extreme, you have sexually transmitted infections where you need a very intimate contact in order for a transmission to take place. And then it is completely unrealistic to assume that you mix uniformly with others. So let me first start talking about the individual heterogeneities, so connecting to what happens inside your body. One way to deal with this, well, it could also be other, that you group individuals that have similar social activity as well. One way to deal with this is to categorize individual into different groups, and you call them types of individuals, and these are allowed to differ both in terms of susceptibility, infectivity, but possibly also in how they mix, assuming that this is the same in all groups. It could be that you divide it into different age categories, males or females, previous history to the disease and not. So there are a lot of different versions depending on the disease. And what you do then is you define a model where you have some different types of individuals, and then sort of not really in the model, but you must know what fraction in the community that are of the different types, and this is usually the case. You know that maybe 10% or infants, maybe 5% of the population consists of infants, maybe 15% of school children, and the rest of adults, and so on. And then a model that is, well, it could be continuous time model, similar to what was called the general stochastic epidemic model. If you remember that one, people were infectious for an exponentially distributed time with mean nu, which means that you recover at rate 1 upon nu, but then the rate at which an I individual infects a given j individual is no longer beta upon n, but it depends on the type of the infectious individual as well as the type of the susceptible individual considered. So here's an exercise connecting to that. By the way, I have inserted in the course webpage, you can now find answers to nearly all of the exercises from my lectures up until today's lecture. So I don't have answers for my last lecture, which comes in 2 weeks. And this matrix, and then you can build up a matrix with these elements that reflect the mean number of infections that one I individual produces, the mean number of J infected individual that one I infectious individual produces in the beginning of the outbreak. And this matrix is called the next generation matrix. And R0 is then the largest eigenvalue to this matrix. So in general, you have a matrix of components, and the basic reproduction number is the largest eigenvalue to this matrix. So I will not explain how you compute the largest eigenvalue, but this can be done numerically. Unfortunately, there is no closed form expression for the largest eigenvalue in general. However, if the parameter beta ij is such that it splits up to one factor depending on the type of the infected person and another factor depending on the type of this the susceptible individual, then you get an explicit expression for an R0 looking like this. This assumption is called separable mixing, and it is, I guess, not the case in most situations, but perhaps in some situations this is possible. And in this exercise, you're supposed to interpret the two factors and compute R0 for a specific situation, obeying this assumption. So that was if you categorize individuals into different types of individuals. How about if you, for some diseases, households are known to play an important role, in the sense that if a disease enters, if someone in a household is infected, it is much more likely that household members, that the person infects household members than a typical person outside the household. These are quite important. So it's not only what age groups you have contact with, but also if you want to model this, you should define households and allow for higher transmission within the households than between the households. However, this is much more complicated because the households are small, so the randomness within a household remains random. So this is this slide. I should have removed this one. I will not talk much more about the household models in this course. So how treating households is a bit complicated. It is not complicated if you simulate, but to obtain analytical results about, for instance, the final size is quite complicated. And the reason for that is that what happens within each household is random. So you sort of have to compute what is the probability that, let's say, 3 out of 5 people get infected in a household, and you do that using the quite complicated formula that I explained at the beginning of the course. And then you have to assume that 3 out of 5 got infected. How many outside the household does such a household infect, and so on. So another important type of heterogeneity relating to the social structure in the community is to model networks. And in particular, this is suitable if you're considering sexually transmitted infections, but also in other situations, the underlying social network is known to play an important role. So what is a network in mathematics is quite often also called a graph. And that is an object which contains nodes and edges between certain nodes. So connecting to the social network, the nodes reflect individuals, and an edge between two nodes reflects some type of social relationship. If you're interested in the spread of influenza, it might be that you are connected to the people that you meet on daily basis. Whereas if you're interested in a sexually transmitted infection, an edge reflects a sexual relationship between two individuals. The social structure is rarely known in detail in any community. Of course, now in social media, you might know the underlying social network for a social media, but usually transmission transmits in sort of real world networks, not networks in social media. Yes, and these are very rarely known in any detail. But so what you do then is quite often you treat the network as random, because whatever things you don't know, a convenient way to model that is to assume that they are random, but you might know some type of structure. For instance, it might be that you know either how many friends on average people have, or else you might even know the sort of the distribution of the number of friends. That is called the degree distribution. So you might know that, well, if it is sex partners over a year, maybe you know that 50% did not have a single sex partner, so the degree probability, the probability to have degree 0 is then 0.5, and maybe 30% had one partner during a year, so then the probability to have degree 1 is 0.3, and then maybe 15% had two partners, so the probability to have degree 2 is 0.5, and so on. Another thing that you might know about the underlying social network is the amount of clustering. And clustering is quite often defined as the fraction of my friends that are friends themselves. And there is another thing called the correlation of degrees in a randomly selected friendship. So the degree correlation reflects whom people interact with. So a positive degree correlation means that socially active people, people with high degree, tend to mix with other people of high degree, whereas a negative degree correlation reflects the opposite situation, meaning that an individual with high degree typically connects to individuals with low degree. So if you want to think of a sexual network, a positive degree correlation might be one where there is a group of individuals, perhaps people between 18 and 25, that are much more sexually active. So that would reflect a positive degree correlation. A negative degree correlation could, for instance, be if there's there's a large amount of prostitution. So prostitutes are the ones that have high degree, and they typically connect with individuals that have low degree. So it could be that you know some features of the underlying network, whereas most other things of the underlying network you don't know, and you treat them as random. So that would describe the underlying social network, and then you define a model for the disease spread on such a network. The simplest model of all is where you infect each of your susceptible friend, you infect independently with some probability P, and then you recover. This can be illustrated in the graph that you can think of that you remove each edge with probability 1 minus P, and the remaining edges would then reflect friendships with potential spreading. So if this is the original social network and you remove each edge with probability 1 minus P, maybe the resulting edge system would look like this, and then the remaining black edges would be ones where transmission would take place. But this is maybe a bit too mathematical, so I will not follow up on this. but instead I will give one case study for this situation, and it's a fairly important case study. And this is where all you know about the underlying social network is the degree distribution. So you know how many what fraction of the community that have 0 friends, what fraction of the community that have 1 friend, what fraction of the community that have 2 friends, and so on. And that is all you know. So you treat the rest of the network as completely as random. So beside knowing the degree distribution, you assume that people mix uniformly. And you have this infectious disease model that is defined by saying that you infect each susceptible friend independently with probability P. And you start off with one randomly selected index case, and the rest in the community are susceptible. So then my question to you is, what is R0? Of course, this is not a live session, but I have given this slide, I think I've given presentations at least 50 times, and I managed to get people to guess in the way I want, or people guess the way I believe in all of these situations. So remember, what is R0? It is the average number of infections caused by a typical individual in the beginning of the outbreak. So suppose that the degree distribution is such that the mean is 4, let's say, and suppose that the transmission probability is P is equal to 0.5. What is R0? Everyone would guess that R0 is 4 multiplied by 0.5, so 2. And more general, the guess would hence be, so the transmission probability multiplied by the mean degree. Unfortunately, that is wrong. And why is it wrong? Well, in order to become infected, you must have been infected by one of your friends. So if you had degree 4 initially, in the beginning of the outbreak, you were infected by 1, whereas the remaining 3 are typically uninfected. So how many you infect, you should subtract the person you were infected by when you compute R0. So then you would guess that the reproduction number equals P times the mean degree subtracted by 1. However, that is also wrong. And why is this wrong? Well, it is quite easy to understand from the following slide. Suppose here you have 6 individuals here showing how many friends they have. Who would you put your money on was the first person to get infected? I think nearly everyone would bet their money on this person, and no one would bet the money on this person, since this one, if it has no friends, it will not get infected. And in fact, this is correct, and it is such that this person who has degree 5 is 5 times more likely to get infected from this one. This implies that in the beginning of the outbreak, individuals with high degree are overrepresented in the sense that they are an individual with degree K is K times more likely than an individual degree 1. So the degree distribution among people infected during the early stage of the outbreak relates to the original one as some proportionality constant multiplied by K times PK. This looks a little bit complicated, but all it says is that this individual is 5 times more likely to get infected compared to that individual. And the basic reproduction number is P times the mean of this shifted degree distribution subtracted by 1. And in terms of the original degree distribution, this mean subtracted by 1 equals the mean of the original degree distribution plus a factor which depends also on the variance of the degree distribution. And the variance perhaps not everyone knows what the variance is, but that it has to do with how random the degree distribution is. In particular, if the degree distribution has a heavy tail, meaning that a few individuals have very large degree, then this term here will dominate. So implying that even if the transmission probability is small and the mean degree is small, this factor can be large, implying that R0 may be large even if both P and the mean of D is small. And in fact, it is also known by sociologists that for nearly all social networks, and for that matter other networks as well, they tend to have heavy tail degree distribution. So this is bad news in the sense that then R0 will be big. Suppose that we would vaccinate before an outbreak takes place. What would then happen? Well, this of course depends on who we vaccinate. If you just had one shot of vaccine, who would you vaccinate here? I think most people realize that it is most effective to vaccinate this individual, and vaccinating this person is completely meaningless. But before doing that, let me treat the simpler case that we vaccinate randomly. Then the new reproduction number is the old one multiplied by 1 minus v. And this is the case that if you on average infect R0, if infectious people on average infect R0 individuals before vaccination, then it is only a fraction 1 minus v of these that are unvaccinated. So the new reproduction number is 1 minus v multiplied by the old one. And as before, this implies that the critical vaccination coverage is 1 minus 1 upon R0. The problem with this is that if R0 is large, it might be hard to obtain this high vaccination coverage. And so perhaps you can do better. And can we do better? Yes, as I just mentioned, if you vaccinate the socially active people, you can probably do better. However, a problem is that we typically don't know who are the socially active people. But a mathematical model sort of trying to circumvent this problem, not claiming to be fully realistic, but still giving some flavor of effective measures, is called the acquaintance vaccination strategy. So this strategy is a strategy which you can perform without knowing who are the socially active people. And it goes as follows. Suppose that first you choose individuals at random, just as you would if you vaccinated people randomly. However, now you don't vaccinate the randomly chosen people, but you ask them to name one of their friends, and you vaccinate that friend. The effect of this will be that the vaccinees that you reach will not have the community fraction of degrees, but they will have this degree distribution among the initially infected. That distribution is called the size bias degree distribution. So using this strategy, you're much more likely to vaccinate people with high degree because they are more likely to be named as friends in the first stage. So this is a much more efficient strategy, which can be illustrated, for instance, here. It's a little bit complicated, but here's the vaccination. Here's the uniform vaccination coverage. This is how many that will get infected for a specific situation and a specific network. I chose a heavy tail network. And if you and here as a function of what fraction you vaccinate, and we see that if we vaccinate around 75%, there will be no outbreak. So the critical vaccination coverage is about 75% if you do uniform vaccination. However, if you do acquaintance vaccination, it is enough to vaccinate 50% of the community. So by doing this acquaintance vaccination, you can do something which is more effective. So what are the conclusions from this this illustration? Well, the main conclusion I would say is that not only the mean number of partners is important, but also the variance is important for determining R0. And as a consequence, core groups, meaning individuals with high degrees, play an important role. And the large variance in the degree distribution imply a large R0. However, it does not necessarily imply that the outbreak will be large. I will come back to that later. Okay, let me take a short break.